Alright, so today we're going to look at specific heat capacity. Okay, so that's cool. And we're also going to look at specific heat capacity for water in particular. And we'll compare it to some other stuff. And by the end of this day, you should be able to say what specific heat capacity is. And how would you calculate it for any substance at all. Basically, you're also going to outline the impacts of, or the implications of the specific heat capacity of water for the environment. Now, we've already covered this. We didn't use the correct terminology because we weren't quite there, but that's where we're heading. All right, so let's go for it. Now, what is specific heat capacity? Basically, it's the amount of energy or heat needed to raise the temperature of 1 gram of a substance by 1 Kelvin degree, which is the same as 1 degree Celsius. It's just zeros for 273 degrees further back. All right, so the symbol is C, capital C, but the unit is joules per gram per Kelvin, and that should give you some clue as to what the formula is going to look like, which we have over here. So the equation for it is the specific heat capacity equals a change in heat divided by the mass times the temperature rise, or temperature change. That should just be temperature change, it doesn't matter. Alright, so we would write it like this. C equals delta H divided by mass times temperature. Okay, so the specific heat capacity, you would get this from an experiment, basically. The specific heat capacity of water is equal to the amount of heat in joules that you put into the experiment, you put into the water, and then the mass, that should say mass in grams, that's insane. We'll change that. So mass in grams. So the mass of grams of water you have, so if you put 100 mils, that's 100 grams of water, and the change in temperature. Okay, so that's what this means, by the way. Delta here, this triangle, which is like a triangle like that, but it's thicker on that side. That means change. So change in heat divided by mass times the change in temperature. All right, so let's have a look at it. Water here you can see, has a really high specific heat capacity. Okay, so it's at 4.18 joules per gram per Kelvin, per degree Kelvin, and ice has a lower one. Aluminium has quite a high specific heat capacity. Glass, iron, copper's not near as high. Silver's very low, lead's very low, and if you look at lead and silver and copper, they're fantastic conductors, whereas glass is a terrible conductor of heat, so it doesn't raise very well, and amazingly, aluminium's really high. Okay, so I think that one might be incorrect. We might need to check that one. So the implications for the water specific heat capacity, what does this mean? Water needs more heat basically to heat it up than other substances do, to raise its temperature. So boiling water is actually a lot less efficient than, say, burning alcohol. So the same amount of heat absorbed by water will raise its temperature less than other substances. So if you put two substances on an equal source of heat, water, compared to a lot of other things, will raise its temperature much, much slightly because it's able to absorb heat. So specific heat capacity is the amount of heat energy that water can absorb. So the temperature of water in an aquatic or marine environment, it changes much less. It's fairly stable compared to, say, the terrestrial environments that they get the same amount of heat. So the same sun rays bounce on them, and there's much more variation. All right, that's reasonably straightforward. All right, we'll see you in class, and bring questions. I think you'll have some after that one.